Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHGTool Cloud. And today we will be going over another exercise, another example of how you can use GHGTool for your own geothermal design. Now we talk quite a lot about theory and methods on this channel, but in the end, if you really want to understand how you can design a bore field, you need exercise, you need practice. And that's why in this series we also show you a couple of exercises, we go over a couple of case studies so you can learn certain things about them and apply them for your own projects. And today we will be looking at a bore field for a single family building. So this is the example building we have. It's a single family house and the goal of this exercise is to learn what the difference is when you design for heating versus design for cooling. So typically, historically, ground source heat pumps bore fields were designed to cope with the heating demand of the building, and cooling was more nice to have. But in more prestige buildings, in more hotter areas, more affected by climate change, cooling is not so much a nice to have, but more a design constraint. So this needs another design methodology, needs another bore field design. So that we will focus on in this video. We will learn a little bit about the difference between active and passive cooling. We will learn about the flow rate and connection in series, and also the difference between the heat pump power and the building demand will be discussed. So let's go over some input parameters. The minimum average fluid temperature is 2 degrees C, and the maximum depends on whether we use active or passive cooling. We will simulate for 40 years, so we have a long horizon, so we have a robust design. And we will start the simulation in January. We have a very homogeneous ground, just basically one layer of 1.9 watts per meter Kelvin between 50 and 200 meters. The volumetric heat capacity is around 2.4 megajoules per cubic meter Kelvin, and the project is located in the Belgian city of Antwerpen, hence the location Bel Antwerpen. For the bore field, we will use a rectangular bore field, doesn't really matter actually, with an initial design of 3 boreholes of 90 meters borehole depth. For resistance, I will use a double DM32 with a borehole of 140 millimeters. We will space the pipes exactly in the middle of them, and we use a slightly better thermally upgraded grout of 1.8 watts per meter Kelvin. For our fluids, we use 25% volume percent of monopropylene glycol, and we will use a flow rate for the entire bore field of 0.7 liters per second. Now, this last one will be important in this exercise. I come back to that later. And lastly, for our load, we use a ground source heat pump which is modulating and has a power of 12 kilowatts. But our building demand is only 9.2 kilowatts in peak and 12 megawatt hours per year in heating demand. For cooling, it's 8.7, which is rather high. But that's also a little bit the exercise of today, but you can see that there's quite a lot of glazing, so a quite high cooling demand, but in our climate zone it's typically slightly less energy demand. So although the peak cooling is not that much lower, the energy consumption is. We have 2 different efficiencies, whether we're working with active or with passive cooling, and we have a certain domestic hot water consumption. So next we will jump into GHGTool and I will show you how I would solve this problem, but to really get most out of this exercise, I suggest you click the video description open, you go to the article, you read the design questions yourself, you try it out with GHGTool, and then you can come back and watch or read in the article what solution I would propose for this problem. But really the key in learning how to design bore fields is by doing it and by experiencing the different physical behaviors yourself. So I'm looking forward to seeing you in GHGTool. So here we are in GHGTool. I created a new project and let's start filling in the information we discussed earlier. So let's stick for the moment to 17 degrees. Let's the simulation period was 40 years. Our ground, we had a conductivity of 1.9, with our project being situated in the city of Antwerp. For borefield, we used a rectangular borefield of 1 borehole by 3 with 90 meters deep. Now, please note we said it's a rectangular field, but of course you can also enter it as a line. It's the same for 1.3. For resistance, we used a double DN32 with a terminal conductivity of 1.8, and for our fluid test it was 25% of monopropylene glycol with a flow rate of 0.7 liters per second for the entire bore field. Now, this difference is important because your flow rate, and we will create a whole separate video specifically for that topic, is determined by your heat pump and by your building demand. So check in the documentation what actually the flow rate is of your heat pump. And this flow rate will be divided over all your boreholes. And the important thing is, since in this exercise you will vary the number of boreholes, that you enter it for the entire bore field, because if you have more or less boreholes, the flow rate for each borehole actually changes. So if we enter it per borehole and we say, well, it's not 3 but 4 boreholes, the flow rate for our entire system would change, which is not something that would happen in practice. So therefore, pay attention, enter it as for the entire bore field. And lastly, we have our thermal demands. So we had domestic hot water of 2,100 kilowatt hours per year. Our efficiency was 4.87 and 3.13 for domestic hot water. Now for monthly loads. We have a heat pump of 12 kilowatts, which is modulating, and we have a building demand of 9.2. So since the heat pump is modulating, it can deliver 9.2 kilowatts. So just use 9.2 in this case. We will come back to that later with a yearly demand of 12,000. And for cooling it was 8.7 with 6,100 kilowatt hours per year of cooling demand. Let's go ahead and simulate this first scenario and see what we end up with. Basically, the way you typically design a bore field historically. So what we see here, it's designed for heating, let's say. We stay slightly above our threshold of 2.22 degrees Celsius, but our cooling demands cannot be met, or our summer comfort is not guaranteed because we cross quite significantly our threshold of 17 degrees for passive cooling, which means that on warm summer days, it's not feasible with passive cooling to really cool your building or to cope with the 8.7 kilowatts of cooling demand. What you can also see here is that our Reynolds numbers are also in cooling slightly below the threshold for transient flow. So our effective borehole resistances are more or less the same. If you have not watched our video on the effective borehole thermal resistance, it's linked in the description below. Also the one with variable fluid properties, we also linked it below. So let's say this is our first scenario. It was designed for heating. It's a traditional way. But now if we say, okay, we really want to be able to ensure the summer comfort. So let's call this scenario 2 and say, well, let's go for, let's call it passive cooling. And we really want to make sure that this temperature stays below the limits. So what we're going to do is we're going to say, well, GHG tool, calculate me the required borehole depth. And what it will do is it will keep the 3 boreholes. It will vary the depth until we end up with a system which can actually cope with this passive cooling demand. And as you can see, we end up with a gradient error. Now, this is an error you will see quite a lot if you work with required borehole depth. We have a whole video about this. It's also linked in the description. But what it basically says is, well, our first scenario was not enough to cope with the cooling demands, so our 90 meters was not deep enough. we here increased the depth iteratively, but when you increase the depth, the ground temperature also increases because we have a temperature gradient. And when the ground temperature is higher, it becomes harder to cool. And it can happen quite often that there is simply no solution for this. So what we do is we say, okay, with 3 boreholes it's not feasible, perhaps it is with 4. So let's go ahead and calculate it again. And this is what I mentioned with the flow rate as well. If we go from 3 to 4 boreholes, now we're safe because we entered the flow rate for the entire bore field. But if you enter it per borehole, this would actually mean that a flow rate is now different between the different scenarios, which is not a good thing to be able to compare them afterwards. And this is the result. We are able to keep the fluid below the 17 degrees, so we are safe with our passive cooling, but we need 4 boreholes of almost 150 meters deep, with a whopping total borehole length of 590 meters, which is more than double the one we had before. So how come? Well, first of all, we have a couple of effects. The ground temperature in this case is 12.35, where here it is 11.3, let's say. So it's 1 degree warmer, meaning that all the lines shift up by 1 degree, making it harder to cool, which is why we also need more borehole lengths. But the second thing is that since we now use 4 boreholes instead of 3, our flow rate is divided by 4 instead of 3, meaning that our flow rate is also significantly lower than it was in our scenario 1, which means that our effective borehole thermal resistance is also higher, meaning it's harder for this bore field to actually exchange heat with the ground. And we cannot change the flow rate of our entire system because it's determined by our demand. But what we could do, for example, is, let's call this scenario 3 series. And now I basically spoiled what I'm going to do, is say, okay, let's go ahead and say we put these boreholes, we have 4 of them, we put them in pairs of 2 in series. So what this will do is that instead of dividing, let's make this slightly bigger, instead of dividing your entire flow rate over 4 boreholes, we now divide them over 2, meaning that we increase the flow rate through each system. And as you can see, we're therefore in the transient regime, our effective borehole thermal resistance is significantly better, and we now only need 354 borehole meters. So 4 boreholes of 90 meters, whereas here it was 4 boreholes of 150 meters. So it's very, very different behavior since we now have a higher flow rate. We also have, of course, a slightly higher pressure drop, but that's not that significant since we're working with a double U-tube, which is always a little bit lower in pressure drop. Now this was for the passive cooling case. Let's go ahead and do the same with active cooling. So we go ahead, we go to our first scenario again, we call it scenario 4, and I will call this active cooling. So what we then do is we go to thermal demand, we change now the efficiency in cooling, and we also say 25 degrees as a maximum, and let's calculate the required depth. Now, it is important to note that active cooling for residential buildings, it's not that straightforward because your emission system needs to be able to cope with it. You cannot simply put ice water temperatures of 12 degrees in your floor heating, because then you will get water on your ground. So if you're working with condensing convectors, for example, it is feasible, but your installer needs to take that into account. But what you can see here, if you go for active cooling, we have still a bore field that's designed for our heating load because we do not reach a 25 degrees maximum temperature. So it's very similar to our scenario 1. Also, the total borehole length is quite similar. So that's an important thing to note if investment cost is an issue in your region for your client, but comfort is really, really important opting for active cooling like is typically done in hotter regions, Spain, Italy, Australia, for example, is actually a solution, or can be a solution. Now, a final thing I want to say is, let's go ahead and make a fifth scenario, and let's go for an on-off heat pump. Because what I did before is say, well, we have a modulating heat pump, so we don't need the 12 kilowatts, we can work with 9.2. But imagine you have an on-off heat pump, then this heat pump, it will always demand 12 kilowatts, because it's 12 or nothing. So if that's the case, or for example you have a modulating heat pump and the installer does not limit the power of the heat pump, we need to calculate with 12. And this of course has an effect on our design, because the heat pump now demands more from our ground, and as you can see, for our initial design, here we were above our 2 degrees Celsius threshold, here we are below, significantly below this threshold. So the difference between designing with a modulating and an on-off heat pump is also in this effect, that since an on-off heat pump demands more than a modulating heat pump, if it's oversized, if it's undersized, it's a different story, but if it's oversized, you also need to oversize your bore field. So that's really important to give to your installers or to your client, that if they install too big a ground source heat pump, that your ground system, your bore field, should also follow, which is of course a bigger investment cost. So this was basically everything I wanted to say about this rather small project. We discussed the difference between modulating and on-off heat pumps. We looked at how the design changes if you go to a passive design. You can optimize that passive design if you, for example, put boreholes in series. This has some practical issues related to air in the system, but that's another story. We also talked about the difference between passive and active cooling, and I hope you can get some insights out of this video and apply them to your own project, because it's really in trying different things, in playing with the software, creating different scenarios that you learn how these systems behave and that you can become better at designing them. So if you think this is interesting, share it with your colleagues, with other companies, follow us on LinkedIn, on YouTube, follow our knowledge base, try out Cheat Tool, and I'm looking forward to seeing you in the next video. Take care. Bye.